Alright, welcome back to us talking about thermodynamics. I'd actually, a little bit of a confession, I don't like thermodynamics, so it's hard for me to get motivated on this stuff. I'm getting excited for the next chapter. I like quantum mechanics, that's the fun stuff. But, I mean, chemistry is such a broad topic. It's like a historian says, oh, I hate covering the American Revolution. My students they tend to prefer thermochemistry because it's very straightforward. That's nice, I guess. I like the little more exotic things. Anyways, let's go talk about school again. So here we are, stoichiometry involving change in enthalpy, delta H. A liquefied petroleum, whatever. Liquefied propane, there we go. Liquefied propane tank in a home barbecue contains 13.2 kilograms of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. Okay, so we have this reaction here, and if you look at it, this entire reaction as written produces minus 2044 kilojoules. So when we do stoichiometry, what's nice about this one, it's a one ratio. There's a single unit there in front of the propane. Let's say you had five moles of oxygen would be required to generate that minus 2044 kilojoules. So, but keep that in mind. But this one, it's more straightforward. So how do we do this? We have 13.2 kilogram of propane, C3H8, 1,000 grams per kilogram. Then we have to do the molecular weight. So carbon is 12. 3 times 12 is 36, plus 8 is 44. Is that right? 44 grams per mole. So then, let's see here. Now we have mole C3H8, C3H8, and then we have minus 2044 kilojoules per mole propane, C3H8, as such. And you can see the units all cancel. Kilograms cancel, grams. Oh, wait, oh, shoot. I'm glad I noticed this. I'm glad this is why it's good to check the units. Check your units, students. Otherwise, you might say something embarrassing on YouTube. And then the moles cancel. So, and throw that in your handy dandy calculator, and you get a minus 6.12 times 10 to the 5th kilojoules. So that's the answer. So 600,000 kilojoules. So that means you can take 600,000 kilograms, so 600 metric tons of water, 1 degree Celsius with that heat. That's a lot of heat, right? So that's one thing you see these reactions. There's a lot of energy in these things. Okay, so recap with this one. We're using stoichiometry involving delta H. And maybe I'll move this thing over to give it a little more room. So you can say it equals. So this one here is still dimensional analysis, and but with this you're including the concept that the chemical reaction now, there's stoichiometry involved in calculating heat flow and setting it up, and you put that in there, and it's and the stoichiometry is in this step right here, and it's a 1 mole propane to that entire mole reaction, minus 2044 kilojoules of energy. Okay, moving on. measuring heat of reaction, a coffee cup calorimeter. So magnesium reacts with hydrochloric acid. In this experiment, we determine the enthalpy change. This reaction, 0.158 grams of magnesium is put in excess HCl to make 100 milliliters of solution. The excess HCl and temperature rises from 25.6 to 32.8. What is the delta H reaction? Delta H for this reaction as written. Use 1 gram per milliliter as the density of solution and specific heat capacity 4.18 joules per gram degree Celsius. Okay, so this is going to be very similar to the last lecture on the bomb calorimeter, except this time heat flow is mass times specific heat capacity, time change in temperature. So our mass here, but the mass is going to be the mass of the solution. So we have 100 milliliters, and it's 1 gram per milliliter. So I'm just going to go ahead and say it's 100 grams. I'm getting that because it's 1 gram per milliliter and 100 milliliters. So it's 100 grams. 100 grams specific heat capacity, and this is the water, 4.18 joules per gram degree Celsius times the final minus the initial, 32.8 minus 25.6 degrees Celsius. And in doing that, we find that the heat flow here is 3,000 joules. So 3,000 joules. Okay. So now let's think about the heat flow. Heat flow for the system, well, it depends on who define the system. The magnesium metal is exothermic, so that means the delta H reaction is negative. Okay, so which means then our heat flow is negative 3,000 joules, and this is per how many grams? 0.158 grams of magnesium, and then the mass of magnesium, is it 24? What is it for magnesium? It's 24.31 grams magnesium per mole magnesium. Units cancel, and we are left with minus 4.6 times 10 to the 5th joules, and per mole magnesium. Usually write it in kilojoules, so this is minus 460 kilojoules per mole. How many sig figs do we have? Looks like we have 3. I would leave it like that. So, or you could say 4.60 times 10 to the minus, or 10 to the 2 kilojoules per mole. Book's giving us 2 sig figs. What are you doing that for? I don't see 2 sig figs. I see 3. All right. We will leave it like that then. Okay, recap with this one. This is similar to, and this is also a limiting reagent problem, by the way, but it's a excess limiting reagent problem. The magnesium metal is the one that's the limiting reagent. But okay, we have the reaction react, and the magnesium is heating up the solution, so we know that it's exothermic. So make sure the heat flow is exothermic, and then we use the heat capacity of the water, because the HCl solution, that's the one that's going up. So we're tracking the heat that way, looking to see how much the solution has warmed, and we find the solution has absorbed 3,000 joules of heat, which means that the magnesium left 3,000 joules of heat, and that's per 0.158 grams of magnesium. And so now we multiply by the atomic mass of the units to get the minus 460 kilojoules per mole from this chemical reaction. Okay, so moving on, let's look at rules with delta H. So if a chemical reaction is multiplied by some factor, then delta H reaction is also multiplied by the same factor. Makes sense. If I can, and you probably make this make sense with your car, right? So if I know that my car gets 25 miles a gallon on gasoline, if I have 2 gallons of gasoline, I can go 50 miles. So I know that if I have half a gallon, I can go 12.5 miles, right? 25 divided by 2. That makes sense. If a chemical equation is reversed, delta H changes sign. This also makes sense. Plants photosynthesize to make sugar, and when I burn that sugar, I'm taking that energy that the plants rightly took from the sun, right? So the energy in is the energy out. So that's why I eat green leafy vegetables, I suppose. And last one is if a chemical equation can be expressed by a sum of a series of steps, then the delta H reaction for the overall equation is the sum of each of the steps of that reaction. So the sum of the heats of reaction for each step. And this is known as Hess's law. And I think these are fun. I like puzzles. These are puzzles. If you think of this as a puzzle, you're going to have fun with it. If you think of it as terrible math that makes no sense, then you're going to hate it. But the idea here is, so let's say that we have A plus 2B goes to some intermediate C, and then intermediate C decomposes into 2 times D. So the overall reaction, A plus 2B makes 2D, is the sum of all the steps. So let's do Hess's law. Okay. Like I said, these are fun. I'm excited. So, well, also, I should say this. When you're doing these problems, everything is presented to you very, very nicely. Okay, so if you're in the real world, if you are tasked with something, there's a saying. There's a saying that a day in the library will save you a month in the laboratory. So if you can look things up, and rarely do things when you're trying to find information like that, rarely is it presented so clear. You have to go through and you have to hunt for things, and you have to be strategic in how you find things, and and you can look at what people have done, and the fact that enthalpy is path independent, and you can make up some fictitious way of doing something, and it should work out. So, and here's one of them. So we have what is the heat of formation of propane? So if we take 3 carbons and 4 hydrogens and we react them to form propane, what is the heat of this reaction? We don't want to measure it, but what we're really good at is burning stuff. So we burn some propane, we burn some carbon, burn some hydrogen. You know what? I might actually stay out of the library to do this experiment. That might be fun. But we burn a bunch of stuff and we measure the temperatures. Oh, someone's already done that. Oh shoot, someone's already done that. So that's okay. But we burn that, and now we can use this information to figure out the heat of formation of that. So when I do these problems, first thing I do, I assign numbers to the enthalpies. I've called the first equation H1, second one H2, third one H3. That's just easier. The other thing I do is I rewrite these equations, putting the products on the right and the reactants on the left. So the first equation here, the combustion of propane, I need to put propane on the right. So I'm going to write 3CO2 plus 4H2O yielding C3H8 plus 5O2. Okay, and this is minus H1. I'm putting a minus here because I flipped the equation, right? That's rule number 1. Next one, I'm going to leave it as is. Carbon plus oxygen makes CO2. And the last one I'm going to leave as is. 2H2 plus O2 makes H2O. So we're having H2 and H3. Okay, now the next step is we have to multiply them by numbers. and in the end, we want this one. So I'm going to multiply the top equation by 3. And I'm going to multiply the bottom equation by 2. Now, I'm going to sum them up. So let's look and see what happens. Oh, wait, this is... Let me just get out of this. It's 4 waters. I forgot to put the 2 in front of the y. It's 4 waters multiplied by 2. So notice, and I apologize if you're colorblind. The waters here, the 4 waters will cancel. And what I'm doing is I'm adding these 3 equations. The 4 waters cancel. And what else cancels? We'll have the CO2 be pink. The 3 CO2s cancel. Now, what do we have? It will be orange. So 5iO2, 3 plus 2 is 5O2. These things right here, and these 3 right there, these also then cancel. Okay, and then when we add together, we get 3C plus 4H2 yields C3H8, which is what we wanted. Right, we wanted that, and it's going to be, minus H1 plus 3H2 plus 2H3, and that means it's minus a minus 2043 plus 3 times a minus 393.5 plus 2 times a minus 483.6, and then we put that in our handy calculator, and we get minus 105 kilojoules per mole reaction for that. Okay, so recap for this one. We have Hess's law. We have we want to know what 3C plus 4H2 making C3H8Hs, but we know these 3 combustion reactions. So rather than try and do this experiment, we're going to use the path-independent nature of enthalpy. And so we go through, and the first equation we flip because the propane needs to be in the product side, and then second and third equation we leave as is because they are the reactants are on the correct side. So then we try and figure out, okay, in this case I'm going to see how do I get the reactants, and I need 3 carbons, start with 1, so I'll multiply the middle equation by 3. I have 4 hydrogens, there's 2 in the other one, so I multiply the bottom equation by 2, and also all the intermediates cancel, and then I get minus of the heat of the first reaction plus 3 times the heat of the second plus 2 times the heat of the third to give us the answer of negative 105 kilojoules per mole reaction. Another strategy you can have with this, if you want to look at eliminating, so you can look at these CO2s, you can try and eliminate the intermediates. That's the other way you can approach this, if you want to do it that way. Okay, let's see if you can solve this one. Delta H for N2O plus NO2 making 3NO. And we have these 3 equations right here. So let's see if you can solve that one. And I'll do this in front of you, so it's fun. So try it now, put it on pause. If not, okay. So the first equation, NO2 is a reactant, so 2NO2 yields 2NO plus O2. And so this is minus H1. And then the second one, NO is, we're going to leave this one because NO is in the right place. N2 plus O2 makes 2NO. This is H2. And N2O is in the right space. N2O yielding 2N2 plus O2H3. Okay. So, how do we do this? Oh wait, am I doing? Oh wait, yeah, that's fine. Oh, this is a 2 here. Do I have everything set up correctly? Okay. Now, for this one here, I'm looking more, how do I get rid of the intermediates? So, right, we have the oxygens here, and we have the nitrogens here. So I have one nitrogen, one oxygen on the left, and I have 2 of each on the right. So the obvious answer is I'm going to multiply this equation by 2 to get rid of those. Now I'm going to add these together, and this adds together to have 2 O2s. I should change the color. I'll do purple. So these 2 O2s cancel here, and I'll do green. These nitrogens cancel there. And now I have 2NO2 plus 2N2O, yielding 2 plus 4, 6NO. And I have H minus H1. Oh, I forgot to put the 2. Plus 2H2 plus H3. And I'm doing something wrong here. I need to divide it by 2. So I have NO2 plus N2O making 3NO, which is what we're after, and it's minus H1 plus 2H2 plus H3 divided by 2. So that is, let's see here. This is 131 plus 2 times 186.6. So plus and minus, oh wait, 163.2, 341 divided by 2. Oh, I'm doing something wrong. Okay, I just wanted to check my calculations real fast, and this is 157.55. So that's the answer there. Okay. I always like the strategy better than the numbers anyways. Okay, so we got one more section in thermochemistry. See you for next time.